Okay, this week we're really diving into quantitative biomechanics. So we're going to start by learning about linear kinematics. And we learned last week that kinematics briefly means describing motion. And there are different ways that we can do that quantitatively. So by the end of this lecture video, we'll review the different types of motion, which we saw in week 2, I think. We'll learn about position and how to calculate and differentiate between distance traveled and displacement. So what is motion? It can be defined as the action or the process of a change in position. And motion or movement is a change in position. Two things are necessary for motion or movement to happen. Those are space and time. We need space to move in and time during which to move. And movements can be classified 3 ways, as we've seen. There is linear, there's angular, and there's a combination of both, which is general motion. So here's an example of rectilinear motion. So all the shapes here are moving in a straight line. That's rectilinear motion. Now, here's an example of curvilinear motion. All the points on each of these shapes move in the same direction. They move the same distance and at the same time, but the difference here is that the path that's followed by the shapes is curved. So this is deemed curvilinear motion. And here we have angular motion or rotation. So as you can see, all the points on the star here move sort of in a circle about that same fixed central line, which is called the axis of rotation. And lastly, we have general motion, which is really just a combination of linear and angular motion. And this video is really just me being extra dramatic in showing you what general motion is, but it gets the point across. So there's clearly quite a bit of angular motion as this football player just backflips down the field, but there's also linear motion here of his entire body going down the field. So this would be considered general motion because there's a combination of both linear and angular motions. So now let's watch this video of a vertical jump, which I think we saw last week as well. But I invite you now to think about what motions are linear and what motions are angular in this video here. So take a few seconds, pause the video if you need to, and write down your answers as to what's linear and what's angular here. So my answer would be that linear motion in this video is the whole body. If we think of it as one point, the whole body just moves up and down. The feet go up and down. The head doesn't really rotate, right? It's just one big movement up and down from the whole body. So that would be linear. Now, in terms of angular motions, I would say that almost all limb movements, the trunk, the legs, the arms, they all rotate about their respective joint centers to create this linear movement. So the angular movement really comes at the sort of limb level. The limbs are rotating, and that's creating a whole body linear movement. So linear kinematics is concerned with the description of linear motion. Questions like speed, distance, and directions, those are all inquiries about the linear kinematics of an object. And the first kinematic characteristic that we might describe about an object is its position. And this comes directly from our definition of motion, which is literally a change in position. So mechanically, position is defined as a location in space. And knowing someone's position is important when you think of players out on the field or the court. And examples of that would be football, tennis, squash, soccer, hockey, rugby, just about any sport where you need to know where other players are on the field while you're playing. That knowing where people are, that is a location in space, and that's a position. So let's start with a simple running example. How would you describe Andre de Grasse's position here? And I've circled or put a blue square around Andre DeGrasse so you know who I'm talking about. But you could describe his position as being 1 meter from the finish line, right? If you estimate the finish line as being here, that's about 1 meter from the finish line. You could also describe his position relative to the starting line, which would be 199 meters from the start if you knew that this was the 200-meter race. So if we explain the position this way, then we've used a measure of length to identify the runner's position relative to some fixed non-moving reference. And in this case, the references were the starting line and the finish line. So if we use the starting line as our reference, then we would say that the runner is at plus 199 meters. And now if the runner was on the other side of the starting line, we describe them as being at negative 199 meters. So we use the positive and negative signs to indicate which side of the starting line the runner's on. And this example of DeGrasse running is only one-dimensional. We're only concerned about one dimension, being the dimension from the starting line to the finish line. So now let's try a two-dimensional situation. So if we're still using this sort of mechanical approach, can you try to guess this player's position on the field here? So this player here. I'll give you a hint. So you can describe his position as being 30 yards from the opposing team's goal line and 15 yards from the left sidelines. But it might also be helpful to actually set up a Cartesian coordinate system to help identify in a more objective way the position or the location of that runner. So let's do that now. The first thing that we do when we build a coordinate system is to locate a fixed reference point. And this fixed point is called the origin because all of the position measurements originate from it. So here I've placed the origin at the intersection of the left sideline and the running back's goal line. So you could choose to put your origin anywhere as long as it's fixed, but I've chosen this spot as being convenient for me. So imagine now that the x-axis runs along the goal line with 0 at the origin and positive numbers to the right of it along the playing field. And imagine that the y-axis lies along the left sidelines with 0 again at the origin and positive numbers increasing as you move towards the opposite goal. So having this coordinate system in place, the player's position is different than what we decided in the slide before. Any thoughts on what his position might be now? So with this coordinate system, we could identify this player's position by saying that he's at position 15, 70. And we're always, remember, presenting the x value first and then the y value. Okay, if we remember our definition of motion, the action or the process of a change in position, then our next task is to discover a way to describe or measure those changes in position. The distance traveled is a measure of the length of the path followed by the object from its initial position to its final position. On the other hand, displacement is this straight line distance in a specific direction from the object's initial position to its final position. And displacement is a vector quantity, which means that it has a magnitude and a direction, whereas distance is simply a measure of magnitude. So let's take our football player again and look at examples of distance and displacement here. So assume that the player received the ball at his 10-yard line after the kickoff, which again was 30 yards from the sideline. So his position at the origin or his initial position would be 30, 10. Now let's say that he ran the ball following this path and he ends the play over here at position 20, 40 on the field. So if we were to go out on the field and actually measure the path that he traveled with the ball, so this squiggly line here, we would measure a distance traveled of 49 yards. Now, if we wanted to calculate the resultant displacement of his trajectory, so again, he's moving down the field we would say that he ran minus 10 yards in the x direction, so in this direction here, and plus 30 yards in the y direction. So remember here that the negative is a sign of direction. So he ran from position plus 30 to position plus 20 in the x direction, giving him a displacement of minus 10 yards in the x direction. And in the y direction, he ran from position plus 10 to position plus 40, giving him a displacement of plus 30 yards in the y direction. Now, we found the displacement in the x and the y directions, and that's great, but we still haven't found the resultant displacement. And that's this diagonal line here, right? This straight line from initial position to final position. So to calculate the resultant displacement, you apply the Pythagorean theorem, and you end up with a displacement of 31.6 yards. Now, I hope you just asked yourself how I ended up with 31.6 yards, and let's break that down now. So on the left here, this is what we know about the situation. We have the player's initial position and his final position, and that's actually enough to tell us our displacement in the x and the y directions. And we do that just simply by subtracting the final position minus the initial position in both directions. Okay, great. So next, we want to find this resultant displacement, right? This hypotenuse here. And we get that by applying the Pythagorean theorem. So I hope you remember this magical formula here, a squared plus b squared equals c squared. So if you plug those numbers in, this is where that magical 31.6 yards comes from. So that's great. Now we have a magnitude, right? A number for our resultant displacement. But we also need a direction because displacement is a vector. So to find the direction, we calculate this angle here that's formed between the initial and final positions. And you've solved all sides of the triangle, so you could calculate your angle however you want. I've chosen to calculate it as the tangent of the opposite over adjacent sides. And I get an angle of minus 18.4 degrees or 18.4 degrees below horizontal. So that's our displacement there. We have our magnitude now and we have our direction. So from this example, we can now describe several quantities of movement. We have the initial and final positions, we have the distance traveled, and we have displacement. And remember that displacement is a vector quantity, so it's always expressed with a length measurement or a magnitude and a direction. And I just want to reiterate for importance the difference between scalar and vector quantities. So a scalar quantity, for example, distance traveled, is a quantity that's only defined by its size or its magnitude. So it's just a number. Whereas a vector quantity, like displacement, is a quantity that's defined by its size or its magnitude and its direction. So a vector always has a number and an orientation. Okay, so to finish off this video, try to answer this question. If someone ran one lap on a 400-meter track, what is the total distance and what is the displacement? So pause the video, write down your answers, try to think through this here. So I would say that the distance is 400 meters, right? Started here, ran one lap around the track. That means a total distance traveled of 400 meters. The displacement, on the other hand, would be 0 meters because they're right back to where they started. Started here, ran one lap around the track, finished at the same position they started, so their displacement is 0 meters. Awesome. So just to quickly recap, in this first video, we reviewed the different types of motion. We learned about position, distance traveled, and displacement, and we are aware of the importance of scalar and vector quantities. So in the next video, we're going to expand on what we learned here and talk about speed, velocity, and acceleration. So I'll see you there.